Today, I would like to give a presentation about peridynamics formulation for Timoshenko beam. The two co-authors are my supervisors, Dr. Erkan Oterkus and Dr. Selda Oterkus. This presentation will contain the following contents. First of all, I will give a very brief introduction about peridynamic theory. Then I will recall the classical Timoshenko beam theory. Next, I will show you how can we derive the peridynamic formulation for Timoshenko beam. And these formulations, the accuracy will verify by some numerical results. And at the end, I will give the final conclusion. So first of all, I will give a brief introduction about peridynamic. So what is peridynamic? Peridynamic is a non-local continuum mechanics theory. The PD equation motion use integration or summation rather than PDE, which is the most popular in the classical continuum mechanics. As you can see, the bottom function. In PD theory, for any certain material point, for example K, will be influenced by all the material points surrounded in a certain domain with finite size. So here Fkj represents the interaction force between material point K and its family member J. The total force acting on point K can be casted by sum up all these interaction force in its horizon. The most advantage of PD theory is that since it is an integration function rather than PDE, singularities can be avoided due to, for example, this continuous displacement field. And based on this feature, PD theory is widely used on solving some discontinuous problem in solid mechanics, for instance, crack propagation and etc. Similarly with the classical theory, the PD equation motion can be also derived from the Lagrange equation. Here, the total kinetic energy T and the potential energy U of the system can be written as following. Here, Wm is the strain energy density function of material point M. Since PD is a non-local theory, Wm in PD should be also written in a non-local form, which means that Wm is a function not only depends on the displacement of material point M itself, but also the displacement of all its family members, like point 1M, 2M, 3M, and etc. So based on this hypothesis, if we substitute all the above equations into the Lagrange equations, we should be able to obtain the bottom expression. The bottom expression is a general form. It is suitable for all the cases if the system is conservative. For this section, we will briefly recall the classical Timoshenko beam theory. Timoshenko assumed the transverse norm of the beam will remain straight during the deformation, and the thickness will not change all the time. According to these assumptions, if we look at the figure at the right-hand side, the displacement field can be written as following. Here the theta is the rotational displacement, and it is independent of W, which is different with the Euler beam theory. Certainly, strains and stresses can be given by the definition and one-dimensional Hooke's law. The strain energy density function W equal to 1/2 strains times stresses. And if we substitute inside, we can obtain the W in terms of displacement only. And note that in order to eliminate z squared, the variable of z, we can integral W over the cross-section and divide it by the area of the cross-section. This will give us the average strain energy density of any certain cross-section of the beam. At this stage, I will show you how can we derive the peridynamic formulation for Timoshenko beam from the Lagrange equation. As mentioned earlier, the PD string energy density should be a non-local function, and the equation of motion can be derived from the Lagrange equation. In order to achieve this, we can start from the classical string energy density function and transform each local terms into the corresponding non-local form. In this page, I'll show you how can we transform the first local term, which is in red color. Here's the procedure. We can tele-expand function theta and ignore the higher order terms, as shown in the first function. And we squared both sides of the function and divided by the absolute value of the side as the second one. Now we consider point S as a fixed point, and we do integration over a substrate domain from minus delta to delta. Actually, this is the size of the horizon. And we will get the following the last two equations. And now we can see that the local terms has already been transformed into the non-local, which is integration or summation form. So next page, we will try to transform the second local term. So similarly with the last step, we can transform the second local term by using tele-expansion as well. So note that here the rotation theta of point X can be taken as the average rotation of point X and its family member. So if we combine these two equations and square the both sides and divide it by the absolute value of theta, which can be also called the weight function or the kernel function. And then we consider point X as a fixed point and integral over the horizon, and we will obtain the last two equations. The last one is the discretization of the integration. Now, if we insert corresponding terms into the classical string energy density function, we will get the string energy density in peridynamic form at a certain material point K. And its family member Wj can be easily written just by the indices cyclic change. As explained earlier in page 5, if we derive the PD equation motion from the Lagrange's equation, we will end up with the third equation in this page. And what we do now is, if we substitute the PD string energy density function, which we just obtained just now, into this function, and rename the summation index, it will give us the final equation motion of Timoshenko beam, as shown the last two equations at the bottom. Here the B theta and the BZ are the body force density corresponds to bending moment and transverse force. So in order to verify the accuracy of the PD formulation for Timoshenko beam, I'll show you some numerical cases, and these results are compared with a finite element results, which are generated by software ANSYS. For the first numerical verification, a simply spotted Timoshenko beam is taken into consideration. As shown in the picture, it's subject to a concentrated force at the center of the beam, and the geometry property and material property are given below. And we can see from the bottom two figures, the PD results agree very well with the finite element result, no matter in terms of deflection or rotational displacement. For the second numerical case, we choose the same beam with same loading, but with clamp boundary condition. And as you can see in the two figures below, the deflection behavior and rotational displacement behavior of PD have a very good agreement with the finite element result. For the last numerical case, again we choose the same beam with mixed boundary condition, left end with clumped and right end with singly spotted. The numerical results are shown in the two figures below, and they are matched very well with each other. So basically, according to these three numerical results, we can say the accuracy of PD formulation for Timoshenko beam are good enough, and they are valid for different boundary conditions. So finally, I would like to give a conclusion. In this presentation, we have seen how can we derive the PD equation motion for Timoshenko beam from the Lagrange equation. So basically, the procedures can be summarized as: first, we write down the classical string energy density, and then we transform each local terms or partial derivative terms into the equivalent integration form by using Tate expansion. Then we substitute by to the Lagrange equation. Finally, we can obtain the PD equation motion. In order to verify the accuracy of the PD equation motion, we compare the PD result to the corresponding finite element result with several different boundary conditions, and the result shows they match very well with each other. And thank you very much for your attention. For any further questions, please feel free to contact me via the email.